In this video, I am going to explain the experimentation of multivibrator, particularly monostable multivibrator, using 555 timer IC. So as you know, basically this 555 is a timer IC. That means we can generate different timing signal out of this 555 timer. So while talking about the timing, different timing output waveforms, it's basically kind of square wave or rectangular pulse. So as a mode of operation in 555 timer, there are basically three: monostable, astable, and bistable operation. Monostable means single shot, so that means you will get only one stable state. Astable means quasi-stable state. Also a stable multivibrator, also called a free running multivibrator. And there is a bistable multivibrator, that is two stable states. Okay, so here in this video we'll see how we can do practical experiment on the monostable multivibrator. Basically I am going to use this MULTISIM, and we'll see the monostable operation of 555 timer in MULTISIM. So let's start. So this is your MULTISIM platform where we'll connect the circuits. So in this project wizard we'll connect the circuits. Okay, so as you know, this multivibrator is an 8-pin IC. So let us see the circuit of the stable multivibrator. So this is monostable multivibrator. This is the monostable multivibrator circuit, where this pin number 1 is ground as per the pin configuration of 555 timer. Pin number 1 is ground, pin number 8 is your VCC, pin number 4 is your reset, pin number 4 is your reset, pin number 3 is the output, and 2 is the trigger input. So monostable multivibrator requires a trigger input, external trigger. So whenever you give the trigger, the negative going trigger, then a pulse will be generated here. I'll explain how this pulse and timing of the pulse here. So this 2 is the trigger input, 3 is the output, 1 is the ground, 4 is the reset, then your 5 is the control input, through which the capacitor is being connected, fixed capacitor which is of 0.01 microfarad. Then 6 and 7, your 6 is the threshold and 7 is the your discharge pin, and both are making common, and through which this capacitor C is grounded. Okay, so in between this 4, 8 and 6, 7, that means the VCC and 6, 7, the resistor R. So the timing of the pulse being generated at the output is being determined by RC, time constant. Okay, it is if you derive the formulation for this, it will be 1.1 RC, the time for which the output will go high. Okay, now to explain so let me explain this more in detail. That is a monostable multivibrator, which is often called single shot or one shot multivibrator, which is can be considered as a pulse generating circuit. Okay, so the pulse is being generated at the pin number 3, that is the output, in which the duration of the pulse, the pulse is being determined by the RC time constant, that is R and C, being connected externally at out of this timer, that is this R and this C. Okay, in a stable state, that means since it has only one stable state, so this during this stable state of this configuration, the circuit is approximate, the output of this circuit is approximately at 0 state. Okay, approximately 0, or ideally it is 0, or logically we can say at the logic level 0. Now when an externally triggered pulse or external trigger pulse is being applied here at the pin number 2, then what will happen? the time then apply the output. When you apply every trigger pulse at this pin number 2, then output forced to go high. Okay, forced to go high, and it will remain high for the time being defined by the RC time constant is RC. It is basically 1.1 RC, 1.1 RC times. Okay, so 1.1 into R into C. So that many times the output will force to high. Once that time elapsed or finished, then the signal or the pulse goes to low. Okay, and it will be remain in the stable state 0 until the next trigger pulse occurs, and again next trigger pulse occurs, again it goes to high, and the waveform continues. Okay, so you can look at this waveform. So if this is my trigger input, okay, at the pin number 2, so when this trigger goes low, that means it is negative going trigger. So when this signal goes low at this pin number 2, that means this 555 timer get triggered in monosode modes, then the output here will force to go high, and it will be remain high for TP time. So what is the TP? TP is nothing but 1.1 R into C. So once the TP time get finished, then it goes low, and once it goes low, this is the stable state, and then it will remain stable or at the 0 state until the next clock or next trigger appears. And when the next trigger appears here, then the pulse again forced to go high, and again it will remain high for TP, and so forth. It is continuing. Now if you look at the voltage at this C, capacitor C, as you see that when the output goes high during that period of time, that is for TP, this capacitor gets charged. So to how up till how much it will get charged? To 2/3 of the VCC. So if the your say VCC is, for example, so 10 volt, then 6.67 volt, 2/3 of the VCC, it will charge. Okay, and suddenly it goes discharge when it goes low. Okay, and the capacitor voltage remains 0, approximately 0, and when the next pulse again occurs, that means during the next trigger or the TP time, because the charging time of the capacitor being defined by the RC time constant. Okay, because the capacitor gets charged through this resistor R. Okay, so RC time constant, it will again charge till 2/3 of the VCC, and when the TP time finished, then it will go down, or during this low going, it discharge abruptly and remain 0, and so forth. It will go on. Let me explain now the operation of this multivibrator from its internal diagram or internal circuitry of the timer. So this is this box. Within this box is the basic internal or primary building blocks of the 555 timer, where you can see there are two op-amps in a mode of comparator. This is used as a comparator, and based on this comparison, output is 0 or 1, and accordingly this is an RS flip-flop. So output of this RS flip-flop is passed through an inverting power amplifier, or simply power amplifier, or we can say the output stage, and from where the output is taking out, and this is also fed to the base of this transistor Q1, and this is your transistor Q2. Okay, so output this base terminal is the reset to make the timer reset. Okay, and internally there is a reference voltage is applied at the emitter terminal, which is the PNP transistor. Okay, this is a PNP transistor, and this is an NPN transistor. Now let's see what will happen. Suppose initially the output is at low stage, that is the circuit is in a stable state. That means, as I mentioned, the output is at low. In case of monostable, when the output is at low, that is the stable state. Okay, then what will happen when the output is at a stable state? That means output is 0, so this Q is 0, base of this NPN transistor is 0, So that means this Q1, the transistor Q1 is, because it is NPN. So this since it is VCC is connected, so this Q1 is on state. Okay, so when this Q1 is on, as you see, this is connected from this the collector of which. So when it is on, this capacitor C is shorted to ground. Okay, this capacitor C is shorted to ground. However, when you apply a negative pulse at this trigger, this is a negative trigger pulse. So when you apply a negative trigger pulse here at the comparator output, comparator input, inverting input, and you see the non-inverting input of this comparator is the 1/3 of the VCC here, and here the inverting of this comparator is the 2/3 of the VCC, and non-inverting is the your threshold input. Okay, threshold input, which is now connected through the resistor R now. Okay, and two 5K internal resistors are being there. So now when C is shorted to ground, however, when you apply a trigger pulse here at the negative input or the inverting input of the op-amp, second op-amp, that is comparator 2, what will happen? The transistor Q1, when you apply here negative, then according to this, okay, so this transistor Q1 will be turned off. So when it gets turned off, then it releases the short circuit. When it gets turned on, turned off, then it releases the short circuit of the capacitor C. Okay, so that means it is not short now. Okay, then when it removes the short circuit or releases the short circuit across this capacitor C, then it drives, because of this removal of the short circuit at the capacitor C, it drives the output to high. Okay, it goes high. So when the output goes high, then what will happen? Because it removes the capacitor grounding, so it starts surging. So how it will start surging? Through this resistor R, because this R is being connected with the VCC. So it starts surging, and as you know, the capacitor get always surged up till 2/3 of the VCC. So the capacitor is now start surging up towards the VCC. Of course, it will surge up till through the up to the VCC through the resistor R. This R here actually I have given it RA probably. No, R. Okay, R. So it surges through R through R up to the VCC, and it will surge the capacitor, the voltage across the capacitor up till 2/3 of the VCC. So then the comparator one's outputs, when it goes, say this capacitor surge up till 2/3 of the VCC, that means when it finishes the 2/3 of the VCC, then the comparator 1 output switch from low to high, which in turn drives the output to its low stage. Okay, so because it turned from low to high, okay, so then because R becomes 1, so it is reset, so then it will output, this Q will be 0. So when it Q is 0, that means because it is R is 1, S is 0, so it becomes 0. Here it is 0. So when it's 0, it is forcing the output to go low state via the output of the flip-flop. Okay. At the same time, the output of the flip-flop turns on the transistor Q1 because it goes low. So it turns on the transistor Q1 on, and hence the capacitor C. So this C get rapidly discharged. So this C get rapidly discharged through the capacitor, through this path. Okay. So the C get rapidly discharged through this transistor Q1. The output of this monostable remains low until the next trigger pulse appears. Okay. So then the cycle is repeats. The waveform is as shown in here. As I explained already, the pulse width of the trigger, that means the trigger input, the pulse width of the trigger input, always remember this pulse width, this negative pulse width of the trigger input should always be less than, must be smaller or always less than the expected pulse width of the output waveform. Suppose here you are expecting, or you required 1 second of pulse here, for example 1 second of pulse here, then this pulse width should be at least less than 1 second here. Okay. Also the trigger pulse must be negative going, so this should be negative going pulse. That means we are talking about this negative pulse width only. Okay. Negative going input signal with an amplitude, so you cannot make the amplitude also should not very high, it should be with an amplitude at least larger than 1/3 of the VCC. Okay, so if your VCC is your 10 volt, for example, if the VCC is 10 volt, then 1/3 of the 10 volt is around 33. Okay, so the time it should be the voltage of this trigger input should be at least more than 3.3. Okay, more than 3.3 volt, at least more than 3.3 volt. And as I mentioned, this time duration for which the output remains high is equal to 1.1 into R into C. So there is a derivation. I am not going to derive that formulation here, you can do it yourself. Okay, so 1.1 R into C, where R is in ohm and C is in farad. Okay, now once the circuit gets triggered at the pin number 2, so the output goes high and it will remain high for TP time. So what is this TP? TP is 1.1 into R into C. But now point to be noted here is that during this TP time, again suppose that next trigger comes within this time, suppose at this point only next trigger comes, then also it will not change its state, remember. Okay, so it will change its states only when next trigger pulse comes. Okay, that means what I mean to say at this point it gets triggered and the output goes high and it will remain high for TP, which is equal to 1.1 into R into C. For example, TP is suppose 1 second, and this is, for example, suppose 0.1 second, just for example. Then after 0.2 or 0.3 second, then next trigger pulse comes, suppose next trigger pulse here. So then also, since it is 1 second, TP is 1 second, so during that 1 second it will not change its states. Okay, so if you would like to change the state within before this TP time elapses, then what you have to do, you have to reset the circuit by connecting the reset terminal, that is pin number 4, connecting this reset terminal into a negative pulse to make it reset. Okay, you can make it reset by connecting a negative pulse at pin number 4, which is the reset terminal. Okay, otherwise this will remain high for TP, that is 1.1 RC, and it goes to low until the next next trigger appears, it will remain 0, and when the next trigger appears it goes high, and so forth, it will go on. Okay, so this is the explanation of this circuit, working of this circuit. Now we'll see this how we can do it in MULTISIM. So this is your MULTISIM these things, MULTISIM platform. Okay, whereas you know this is these are the shortcut of the libraries where you will get different components. Okay, so anywhere you can click and then search it. Okay, so this is an analog pin. So let's see analog IC, that is linear IC, 555 timer. So what are the things we required? We need a 555 timer, 1 resistor, and 2 capacitors. Okay, 1 VCC, then 1 ground, and to monitor the output we need CRO, and for giving the trigger, any kind of triggering pulse. Okay, So let's see. So here anyone you click and then you can search. Okay, so since I have clicked on the diode, it shows the different diode, triangle, LED, all those things, but we can search it there. Simply you just click on the all groups and then you can search it. So I'm typing 555. Okay, so there are different 555 timers are there. So this I mean different types of, so this is directly timer IC. In this platform it is little difficult to connect here, so I will not go to. A similar version of this is this 555 timer. So for connection purpose it is good to use this. And you can see there is a virtual, which is an ideal timer. So this is a rated timer, voltage and current are rated accordingly. Okay, but this is a virtual. Virtual means it is idealized timer. So we are not same only, these two are same only, but this is idealized. We are not going to use this idealized because practically things are slightly different than that of the ideal one. So therefore we will use this rated timer. So this timer rated means it is voltage and power or current and voltage are rated according to the ratings. Okay, so we'll use it. Click on OK. So this is your timer now. Next, what I want to register. From here you select basics. So under this basics you will see this resistor and the capacitor. So I'm just clicking on the resistor. Any resistor, so later on I'll change the value. So this is my resistor. Similarly the capacitor, I need two capacitors, so one capacitor, one more capacitor. The value I'll change later. So this is another capacitor. Then I need VCC, so therefore we'll go to the source, and in the source you can see this the power source. So under this power source you'll see this is your VCC. Okay, I'll use this VCC. And then one ground for ground you can use this VSS also, but we'll use the SSS ground. So we'll use this or with reference ground. Sorry, this ground I'll yes, this ground I'll use. Okay, so that's all the different components. Now let's connect. Okay, so this is your VCC, which is pin number 8. Okay, so this is pin number 8. So from which I'm just connecting this VCC here directly. If you drag and drop, you see when you see this red connecting point, then that means it get connected, or later on also you can connect. Okay, so this E1 is actually the level of this, so I'll put it here. Then what I need to see, this reset pin also being connected to the VCC. So here I am connecting with the VCC. Okay, this is your reset pin connecting with the VCC. And then this surge and the threshold input, these two, this surge and the threshold should be made common. Okay, make common, so I'll make it common. And then this resistor, so I'll flip it, okay, clockwise, horizontally, vertically. So I'll put it here. So this is also being connected in between the VCC or pin number 4 and 8. So I'm connecting it here, and another terminal of this resistor is connecting here. Then what I need, the capacitor, the values I'll change at later time. So this capacitor also I'm changing, rotating. Okay, now this capacitor is connected with this, and then it is connected to the ground. So ground I will connect here. This is the ground pin number 1. Okay, so this ground is here. So this ground I am this capacitor also need to be grounded. So I will connect the capacitor here. Okay, then this control pin I will connect this capacitor. So that is also rotate 90 degree clockwise. So this is connected here. okay, and that is also grounded. That's all. Then okay, now I need one function generator or to give the trigger, so let me give the trigger pulse using a function generator. So let me connect a function generator here in this panel. In the rightmost in this panel you will see different function generator, CRO, DSO, spectrum analyzer, all those machines you will see here. Okay, so once you put the cursor on it, you will see the name. So this is your multimeter, second is the function generator. Okay, I'll use the simple function generator here. So this is my function generator. Okay, you can double click on it later. Now okay, I'll show you. Then multimeter, function generator, then this is your wattmeter, this is oscilloscope, simple oscilloscope, so I'll use this oscilloscope. Okay, then okay, these are the things required. Okay, now so let me connect this positive input of the function generator with this trigger input. I'll set the input, okay, and the common should be connected to the ground here, or you can use separate ground as well. Then the CRO, suppose this is a 2-channel CRO, so I'll connect this output here in the let me connect okay, let me connect the channel A with input, that is trigger input, so I'll connect it here, and of course the negative one should be referred as a ground here. Then the B channel B is now I'm connecting with the output, and the negative here is connected to the ground. Okay, so that's all, the circuit is connected. Now let me change the values. Okay, so first in each component, if you double click, you will get the wizard for changing the different parameters. So let us start with this. So VCC, you double click on it. Okay, so you see these pins, VCC, which is a power type. Then if you would like to incorporate any fault tolerance here, so I don't want, so none. Then the value, right now it is 5 volts, because it is in a timer I see 555, you can give the VCC from 5 to 15 volts, so I'll put it as a 10 volt. Okay, then display, these are different parameters that you can display here in the circuit, no need. And label you can put, so let it be VCC, this is the reference designation. Okay, so okay, then this resistor R1 here, right now it is R1, so let me change it. So for the time being I am making it 10k. Then these are the different labels, so let it R only. Okay, and different parameters you can change here. This okay, these are the temperature coefficient, or according to the SPICE simulation parameters you can change this. Now we are not going to use this. Tolerance also you can use 5%, 10%, right now 0%, so it will be exactly 10 kilo ohm. Similarly fault, these are the pins. Okay, that means 2 pins, one is connected to the VCC, another one is net A, as a net A, I mean according to the SPICE model. And there are different usage fields, you can type it here. Okay, vendor, status, price, all those things, no need. Okay, oh sorry, I did not put it. Okay, so label I'll make it R only, value I'll make it 10k for the time being. Then okay, then this capacitor C2 must be your 0.01, so I'll this should be your 0.01 microfarad, 0.01 microfarad, and label let me put it as C2 for which is no problem, but here this one I'll change. For the time being I'll make it 0.64. Okay, and I'll make it label as C1. Value I'll make it for the time being 0.64. I'll mention why I'm actually putting 0.64 microfarad. Okay, 0.64 microfarad for the time being. Okay, later on I'll change. Now why I'll tell you why I'm giving this 0.64. Then okay, you can change some of this parameter here. These are the different pins, okay, of this timer. Then display you can change, label, this is now labeling as U1, okay. Then come to this function generator. So let me change the parameter of this function generator. You double click on it. This is simple function generator generating the waveform sine, triangular and the square. So what I need a square wave, okay. Then let me put, this is the frequency, duty cycles, amplitude, okay. So for the time being, let me choose here 100 hertz of the pulse, and duty cycle says 70%. I hope you understand the duty cycle. So 70% means the on time of the pulse will be more, that is 70%, and 30% of the total out of the total time duration, that is your 100 hertz. 100 hertz means your 1 by 100, that is 0.01 second. 0.01 second is your time duration of the pulse, total time duration of the signal. So out of that 0.01 second, 70% will be on time and 30% will be off time, okay. So off time means negative going, on time means positive going. Amplitude, okay, let me put it as 10 volt, okay. So as let me put it as 5 volt, because also I have mentioned earlier that this trigger pulse, the amplitude of the trigger pulse should be at least 1/3 of the VCC, okay. So VCC is 10 volt, so at least I can make it 5 volt, okay. So that's it. So that is your, the settings is done. Then CRO, this is your CRO where nothing is to actually set up, okay. Users can change this time scale, then voltage per division of the channel A, voltage per division of the channel B. So during the process I will change it accordingly, and this will show the timing and amplitude of the channel A, channel B, okay. You can save the figure, I mean snapshot. And external triggering, for the time being no external triggering is used here. This is your external triggering, so I will not use any external triggering, okay. So that's it. Now see, as I have given this 100 hertz, okay. I'll just show you the calculation, okay. I'll just show you the calculations. So for the trigger, I'm giving 100 hertz. So frequency I'm giving 100 hertz, okay. So since it is frequency is 100 hertz, so time will be, your time duration of the pulse is equal to your 0.01 second, okay. 0.01 second total pulse. Now since 70% and the 30% I have used, so 70% of this total time will be how much? Sorry, 30%. 30% is the total time. 30% of the total time. So it will be how much? 0.01. So the because this get triggered in a negative pulse only, so the off time I am considering, which is 30%. So off time I am saying off time of the trigger. So off time will be equal to how much? 30%. So so your on time will be 0.003 second. okay, 0.003 second, or say 3 millisecond. Okay, and this is your equal to 10 millisecond. Okay, this is your 10 millisecond, and this is equal to your 3 millisecond. Okay, similarly on time, so likewise on time will be, since 3 millisecond is off time, so on time of the pulse, trigger pulse, is equal to 7 millisecond. Okay, 7 millisecond. Now the output TP, okay, TP, the pulse width of the waveform on time, this is equal to 1.1 into R into C. So which will be equal to 1.1 into R. How much I have given? R I have given 10K, and R I have given 10K, so 10,000 into your capacitor I have given 0.64, probably, yes, 0.64, 0.64 microfarad. That means it is into 10 to the power minus 6. Okay, so what it will be? It will be is equal to, so this 4, so it gets minus 2. Okay, let me say 1.1 into 0.64, so 1.1 into 0.64, so it is 0.704, so that means it is 7.04 milliseconds. So 7.04 millisecond. Okay, so for the 7.04 millisecond it will remain high. So what I did is, as I mentioned while explaining, that the TP should be at least greater than the off time, or that pulse width of the trigger. So my pulse width of the trigger, because it is negative pulse, so it is the pulse width of that is off time we have to consider, which is 3 milliseconds. Okay, so therefore to make it at least greater than, and for better visualization greater than on time also, I put it as 7.04 milliseconds, so as to in the next trigger it will be again go high. Okay, so that is why. Otherwise you can change this resistor capacitor value. Right now I am giving 10K and 0.64 microsecond, so you can change it. I'll show you. You can change it and can have the different time at the output. Okay, on time of the output. But remember one thing, this TP, that is 1.1 RAC, should be at least greater than this off time of the trigger pulse, or that is the pulse width of the trigger. Since it is negative, that is off time. Okay, so this is the calculations. So let's see here. Okay, so you save it. Okay, let me save it. Okay, let me save it as I have given this monostable one. Save it. Okay, now just run it. So you just run it by clicking here, this run or F5. So it is running. So now you see the CRO. This is your CRO. Let me reverse it so as okay. Then let me change the time scale. So just reduce it so as I can see it better. Then this is overlapping. So let me, this X position, Y position, you can change this. So this Y position select below. This is channel A, so where I have connected channel A, channel A is the input, I mean the trigger, so let me put it up. Okay, so up, this is a channel A, and channel B, let me put it down. Okay, Now the voltage division, so let it be 10. Okay, so 1 division means 1 bigger square is 10. You know all how to operate the serial, the same as you have operated in the lab. Okay, so it is running. So let me pause somewhere so as to check the output, verify the output properly. Sorry. Okay, let me now check. So first of all, the voltage. This is your channel A and this is your channel B. So channel B is A is my trigger input. So this is channel A. Okay. So let me put it in the ground. So from this, because I have given and this as 5 volt. Okay, so it is 5 volt, and because the division is of 10 volt, so it is at the half 5 volt, peak to peak 10 volt. Okay, then the output you will get at least up till 2/3 of the VCC. So VCC is 10 volt. So I'm just keeping it up, almost 10 volt. You see, approximately 2/3 of the VCC you will get. So it is output table. Now I'll see the time. Okay, this because it is the timer, so most importantly is the timing. Now this is to check the time. Okay, so this is one scale, this is another one. Okay, so let me check first the off time of the pulse, that is the pulse width of the trigger pulse. Okay, this is calling it as a T1, the red one, and the blue one is T2. So T1 you see this is 2 point, or it will go slightly this so 3.05 it is okay, so 2.998, that means the 3 millisecond. Okay, as you see here I have given this 3 millisecond. Okay, so you see this is the time. T2 minus T1 is the time between these two, that means the pulse rate. So it is 2.998 millisecond. That is your time of the pulse rate. And on time you can see, so it will be around, because I have given 100 hertz pulse, that means 10 milliseconds. So 3 millisecond goes as off time, so it will be 7. So 7 millisecond. Okay, almost 7. It is okay. And then the amplitude you can see here, if I put it here, so amplitude is 5 volt peak to peak. Then 5 volt means from 0 to 5 volt. Then in the channel 2, channel B, my output, so output is of 10 volt, you see, at this red one. Now let's see the output timing. Okay, so as you can see here, it is negative going of the pulse. So once the pulse goes negative, then the output forced to go high. So this is high, and it will remain high up till TP time second, a TP time period. So let's see this TP is proper or not. So here I am connecting the first red one, and it is at this point. Yes, at this point, this marker, sorry. Now this time gap is, you see, 7.07 or say 7 milliseconds. So as you see here, this is my 7.04 millisecond. Okay, so it is showing 7.07 or 7.04. Okay, so that means this, for this many time it goes on and it goes low immediately, abruptly, you see, for around 3. For around 3 milliseconds it goes low, because by that time the second trigger, so around 3, so by that time the second trigger occurs. Okay, so this second trigger, again it goes high. Okay, so this is what this monostable operation is all about. Then now you can change this value. Okay, let me put it as say 0.1 microfarad. Let's see what will happen in 0.1 microsecond. So let's see what will happen when I'll give it as 0.1 microfarad. Okay, if I give it as a 0.1 microfarad, then as you can see, this TP 1.1 into R into C, so 1.1 into 10K, R is 10K still, so 0.1, so it is microfarad minus 6, so it will go minus 4, then it will be 0.11 into 10 to the power minus 2 the second, and therefore 1.1 sorry 0.11 into 10 to the power minus 2, so therefore 1.1 millisecond. Yes, 1.1 millisecond. Now see, as my off time of the trigger is 3, if I would like to make it fixed at this, since my off time of the trigger, that means the trigger pulse rate is 3 milliseconds and my TP is 1.1 milliseconds, so which is less than this, so you'll see some jitter or the noise here. Okay, let's see. So here I am changing it to 0.1, W 0.1. Okay, you see, and the simulation, oh okay, the simulation is running. Actually make it stop first. Okay, so let me change it as 0.1 microfarad. Then if I run it again, you see this jitter occurs during this negative pulse when it goes. Okay, this jitter occurs. Okay, so that is why at least it is said that it is, this is TP should be at least greater than the pulse rate of the trigger. So since it is 3, so if now you would like to make the C 0.1 microfarad, so what I need to do is I have to increase the resistance. So let me put 20k. If I put, it will be then 20, that is 2 times more, that is 2.2 something only. Okay, then also, so let me put it as 47k. Okay, let me put it as 47k. Let's see how much it will be. Say 47k. That's such standard resistance. Okay, so what will happen in the 47k here? So if I put it 47k, so it will be 47k. Then how much will be the time? So it is 10 to the minus 6. So then the minus 3, 10 to the power minus 3 is there. So that will be 4 millisecond. Okay. Then 1.1 into 47 into 0.1. So let me see. 1.1 into 47 into 0.1. So 5.17 millisecond. Okay. 5.17 millisecond. Okay, let me put it as 5.17 millisecond. Okay, let's see. So now let's see. Okay, now see, the voltage will be remain same only because I have not changed the trigger wave and voltage here. Now the timing. Okay, so this is one negative going pulse here. So let's see here, because this time is remain same, no, I have not changed the timing of the trigger pulse, so it is remain same. So which is your almost 3 millisecond. This is almost 3 millisecond. Then when it goes low, then it goes high, the output goes high, and see for how many times it goes high. Okay, better you put it here. Click on here. Okay. So now it is this time TP. So the time difference is 5.147 milliseconds. So what we obtained here, 5.17. Yes. So 5.147, 5.17, almost same. Okay. So for that many time it goes on, then off. Off is also, you see, almost same. Hmm, 4.8, almost. So by that way you can tune this R and C so as to get a perfect square wave. Number one. Number two, as you can see, during this say suppose this is one complete cycle, or from this one complete cycle, here we are getting another cycle here. So by tuning up this, you can have a frequency divider using this. You can use this multivibrator as a frequency divider. So how to make this frequency divider? So at least you should make this TP greater than the total time of the trigger pulse. Okay, so let me show you that. Okay, total time of the trigger pulse. So my total time of the trigger pulse is 10 milliseconds. Okay, now if I make this TP greater than the 10 millisecond, then it will be your frequency divider. So what I want this TP greater than the 10 milliseconds. So let me put, so suppose if I put here say R say 10K for example, and if I put the capacitor C as 1 microfarad, so then how much it will be? 11 millisecond. Yes, 11 millisecond. Okay, 11 millisecond. So it is greater than the 10 millisecond, and then let's see. So let me put it as the resistor as 10K. By double clicking on it, you can change the variables. Oh, sorry, simulation is running. Okay, so capacitor resistor is 10K, then capacitor I am putting it as 1K. 1K. Okay, then let's run it. So you see, in one pulse there is some jitter. I'll show you. This during this one pulse, two pulse, there is one pulse. So this is one pulse here, and this is one pulse, second pulse. So in which you will get only one pulse. Okay, so from this to this one pulse, and from this to this another pulse. But here from this slightly, it is not perfectly alright, you will get one pulse. That means frequency get divided by 2. Okay, so this jitter is happening because this pulse width TP is far more greater than the pulse width of the trigger. So what we can do is we can increase the frequency of the trigger. Okay, we can increase the frequency of the trigger, or yes, we can decrease the frequency of the trigger. So, let me decrease the pulse width of the trigger. So it is 100 hertz. Let me put it as 50 hertz. Then see. You see, this is perfectly all right now. Time scale, I'll put little more. Now see here, this is starting from this negative pulse, it is one cycle, then from this another cycle. Okay, here in one cycle this is also okay. Just a minute, let me check. So it is 5.882, that is 6, as you can see here. It is 6 millisecond of time. Okay, then this time is 10 millisecond or 11 millisecond. So it will be more than the this TP should be more than the total time. So here it is 6, that means here it is on time will be 14 millisecond. Okay, on time will be 14, so 20 millisecond, it should be greater than the 20 milliseconds. So let me put it as 20k. So if I put 20k, then it will be 22 millisecond, right? 22 milliseconds. So it will be more than the 20 millisecond. Okay, so for 20k I will put 20k, the resistor 20k. So let me put resistor 20k with capacitor 1 microfarad. Okay, then see. So from here if you see, this is one complete pulse, again another complete pulse. So but here you will get only one. So during these two pulse, one up till here, second up till here, so during these two you are getting only one pulse here. So that means frequency get divided by 2. Okay. So this is the monostable operation of the 555 timer. One more application of this is your pulse stretcher. So what we can see here, that this pulse width, also let me put it as 10k, so as to see the things clearly. Okay, so as you can see, this is the negative pulse, and we can make the output pulse of a longer duration than that of this negative pulse of the trigger. So by that concept, it can be used as a pulse stretcher. That means you can stretching out the pulse. So that can be useful for just blinking of LEDs, because often this narrow pulse, suppose with this pulse, if you would like to display a LED, often this narrow pulse with signals are not suitable for driving an LED display, mainly because of their very narrow pulse width. In other words, the LED may be flashing, but it may not be visible to our eye. So we need to stretch it out, this pulse. Okay, so this pulse stretcher can be used to remedy of that problem. Okay, as a pulse stretcher. That can be done easily using simply connecting an LED at the output. You can see. Okay, at the output, if you just connect an LED, you can see it. Okay, so let me connect one LED here. So I will put LED here. Okay, so let me connect this LED here. Now if you run it, you will see this is glowing. That's all. Okay, so that's all about the monostable multivibrator. What you need to do is you need to do this experiment yourself and make a table. What to make a table? Table is, first in the table you should have the pulse width of the trigger pulse. Then in the table, so let us fix this for entire experiment. Then in first column you put R for different values of R. In the second column you put C for different values of C. Okay, then you calculate TP, theoretical, practical. TP, then TP is the on time of the output, then off time of the output you calculate. Okay, TP is the on time, remember. So on time of the, that is the pulse width of the output pulse, and off time, and calculate the total frequency. Okay, so around 5-6 different sets you take up with different values of R and C. Remember, this TP must be at least greater than the off time, that is the pulse width of the negative pulse. Okay, thank you very much.